Hi everyone, my name is Thuan working at the University of Saskatchewan. I am here today to show you a workflow on e-cognition software for plot boundary extraction using UAV imagery. My talk includes an overview of the study and the major challenges, an overview on the workflow, and a live data processing demo in e-cognition. Along with this tutorial, we also have a manuscript, data, and a rule set so that you can get insight and practice on it. At our lab, about 15 terabytes of images on plant breeding were collected each year. So batch processing is necessary for extracting plant phenometrics, and plot boundary extraction is very important for rapid phenotypic data acquisition. As a plot was generated by seeders, the space between plots are inconsistent, and under the effect of experimental treatments and environmental factors, the plots are characterized by high heterogeneity of crop cover. So, our main aim in this study is to develop a workflow for plot extraction using UAV imagery. The input multispectral image were captured on July 10, 2018 using DJI M600 UAV with a spatial resolution of 2 cm. The trial consists of nearly 5,000 plots. On the left, you can see here is an overview of the child in RGB image and the subset in RGB and the NDVI. On the right is the major step of the workflow. From the input image, we rotate the map to the north, and then we calculate NDVI, and image filter were conducted to highlight the plot location. Then, on the dense crop cover, plot were located using NDVI. On the sparse crop cover, plots were estimated by the intersection of the horizontal rows and the vertical rows, which were based on the dense plot that you can see in the red box here. Some adjustments were applied to finalize the boundary map. Here are what you can see in the software lately. A is a subset of the RGB image. From there, we first calculate NDVI, and then live filter will apply on the NDVI to highlight the vertical line, called vertical highlight, as you can see in the bright color here. Highlight horizontal rows by a customized convolutional filter on the vertical highlight. Result in a raster map in C, as you can see here. The red means higher raster value. We will detail this in the live video. The image in C will then classify using local maxima algorithm to get the horizontal rows in green color here. We also get the non-horizontal region in the gray, as you can see. Adjustments were made so that the width of the horizontal rows equal to the length of the plot, as you can see in the green region in E. And from this green region, from the horizontal region in green, dense plot were classified using threshold algorithm, and the output, as you can see in the purple. So from this purple plot, we resize the dense plot, and we get into the purple square here. From the purple plot here, we buffer horizontally to get a coating region in yellow. We do this to prevent any estimated plots located too close to the dense plot. From the dense plot here, we grow vertically to get the potential vertical rows, as you can see in here. In the same way, from non-horizontal rows, we grow horizontally, and the output is here. You can see here is a non-horizontal rows, and by doing that, we leave the potential vertical rows in the horizontal rows. After that, some minor steps to reverse map angle and refine plot size were conducted to get output map, as you can see in the graph here. Stay tuned, guys. In the next section, I will run a demo on and explain more on this in software. Hi guys, now we've moved to the software demo section. On the screen now is the Recognition software with the input image displaying in RGB. This image has 5 layers or 5 bands, and also the fill boundary, as you can see in yellow here in shapefile. On the right is the rule set that we compile to extract plot boundary of the lentil. Overall, we have the 5 major steps here. Step number 1, we're going to define the fill boundary and the rotate image. In the second step, we will calculate NDVI and vertical lines enhancement. Step number 3 going to be horizontal rows enhancement, and the step number 4 going to be plot segmentation. Finally, we will have some refined steps and export the final output. Now I will go step by step to show you in detail. So first is segmentation and assign region of interest. We use segmentation to segment the image into objects based on the input fill boundary, and then we assign that into 2 regions. So you can see here the gray region is the region that we want to work on, and from that we also extract the angle variable of this object so that we can define the rotate angle. In the next step here, we will copy this map and rotate it so that it's going to be parallel to the north. Here is a copy map with a rotate angle of 8.7 degree, and the interested region look like this. Now move to step number 2. First, we start with vegetation index. We're going to calculate NDVI. So from that NDVI, we will inverse this NDVI and mask it to support the line detection algorithm in the next step. So the output of this step includes NDVI map look like this, and then an inverse NDVI map which look like this, and we also have a mask NDVI which is the dense plot look like this. The next step will be the line detection. Basically, we're going to highlight the vertical line from the NDVI inverse using line detection, line extraction algorithm. And here is a specific parameter that I used to do this. Once we have a line detection map in raster, we're going to multiply with the mask NDVI, and the output going to be a line mask raster layer look like this. Here I'm gonna delete some raster layer that I don't need anymore. So go to the line mask. So from there we move to the step number 3, horizontal rows enhancement. We start step number 3 by refine the region of interest or the fill boundary. And then we're gonna run a loop to highlight or to enhance the horizontal rows. So by that, we first have to prepare some temporary raster layer that can help us to hold the computed value from the loop. As this is quite a complicated step, I will go slowly and run one by one for the first loop, and for the other loop it's gonna be the same. So on the region of interest, we're gonna do feature segmentation with a width of 3 pixels. So output of segmentation gonna look like this, which are the square box. Now we will merge the square box which have the same the y coordinate to get the horizontal objects, and the output look like this. Here is the horizontal objects. Now we will calculate the mean value of the raster layer and store it in the horizontal objects, and the output gonna be saved in temporary raster layer. And here is the output. After each run, we will sum up this temporary file into the row raster layer. And then change the size of the horizontal feature or object here with the increment of 5 pixels. And then merge object and then restart it with the new object size. After number of loops, we have rows enhancement look like this. So in the next step, we're gonna find the horizontal line and define the height of the horizontal rows. So we start with object segmentation using the region of interest or field boundary. So from the field boundary, here in the gray color, after that we're going to do checkbox segmentation with the object size of 15. So from here, again, we're going to merge the object which have the same y coordinate together. By so we're going to have horizontal object look like this. After that, we're going to use local maxima algorithm to find the center of the horizontal rows. So from here, we can grow the pixel and define the width or the width of the horizontal rows. This also the length of the vertical rows, as you can see here. So at the end of the step number 3, we have a classified map with the horizontal rows in green and non-horizontal rows in gray. Now we move to step number 4 for plot segmentation. In this, we first use the multi-threshold segmentation on the horizontal region. using the line mask, that means the vertical highlight. So now the dense plot will classify and assign in the purple color. We're gonna resize this plot using pixel-based object resizing. So we're gonna grow this vertically, and you can see that the object will grow vertically, but only on the horizontal region or green region only. So at the end of this then plot segmentation, we have a classification map with 3 classes like this. So this is non-horizontal rows, this is horizontal rows in green, and the dense plot in purple color. Now the next step will be plot extraction for sparse vegetation index. That means in the green area here, you can see there's no vegetation at all, but we're gonna predict it. First, we're gonna buffer this dense plot horizontally. So that the estimated or predicted plot will not grow too close to the existing plot. Then we grow the dense plot vertically. As you can see here, it grows through all the way vertically on the horizontal rows. In the same way, from the non-horizontal rows here, we will grow the pixel horizontally so that we can get rid of the potential rows on the non-horizontal rows here. So now we reassign the class and some other step to refine it. And what I just done is move the buffer class into non-horizontal rows. Yeah, and then move the potential rows into the lentil class. So now on the map we have 2 classes. One is lentil and the other is unclassified. So after step number 4, here's what we have. So we're gonna, next step, we're gonna copy this map back and rotate it into the main map, and then convert this into a shapefile and export it. So here we copy the map back into the main map and go to the main map. You can see here is the output map. We can display in RGB and overlay this. So from here we can convert into shapefile and export it. So what we can have in the output map is a shapefile, as you can see in here, for the whole field. It looks like this. So the final output map with the vector layer look like this. It has been a long process to get to the output map. So if you have any question, please let me know. Thank you very much for watching.